Good afternoon. We have been discussing about construction of the interface. So we will continue that discussion, and after that we will discuss about the measurement of velocity. Okay. So let us talk about interface reconstruction. So while we were discussing the optical method, we understood that if I use a source of light and then within that if some fluid is flowing inside the pipe, and on the other side of the pipe if I use a detector, then depending upon the type of the fluid which I am having inside the pipe, I will be having corresponding change in the voltage signal. Okay, because if you recall from the last lecture, we have seen two types of situation. So in a tank, what we had done, initially we had tried to see different height of water when the top portion of the tank was filled with air, and corresponding to that, when we plotted height versus voltage signal, that was remaining almost the same. Okay, but when air I replaced with some other type of fluid, for example the graph previously shown that was for kerosene. Okay, so now if h is height of water, then remaining portion, which will be, say if small capital D is internal diameter, then this portion is D minus H. So D minus H portion is filled with actually kerosene. Okay, so in this scenario we observed that when H was large or close to unity, corresponding to large H, we were having pure water and we were having the high value of the voltage signal. But once we have started decreasing the H, it means we have started increasing the amount of kerosene in the tank. Corresponding to that, our voltage signal has decreased significantly. Is this point clear? So this thing we have actually seen in the previous lecture. Now we will try to utilize this principle for reconstruction of the interface profile. Okay, like if you have arbitrary signal for this type of detector, then for this arbitrary signal you can tell that what should be the corresponding height of the interface. Okay, and if this type of data you do measure from multiple sources and multiple detectors, then you can utilize that data by using interpolation method for reconstruction of the interface profile. Okay, is this one clear? So if you have a two-dimensional flat interface, so this is the schematic representation of test setup which we will be using for different type of situations in this present discussion. Okay, so this black colored system shows a rectangular box. This rectangular box is having one outlet at this end and one inlet from here. Okay, and this rectangular box is placed on some platform which is having provision for its orientation at an inclined plane. So let's consider at the moment it is shown that it is at an angle of theta. Okay, when you have partially the box is filled with kerosene and partially it is filled with water, and if it is placed on an inclined surface, we have gravitational force acting in the vertical direction only. Okay, so interface between the kerosene and water will be remaining always flat. Is this one clear? So interface will be remaining flat, but if you consider that at the bottom portion you have used a uniform intensity two-dimensional light source. So here you can see your light is nothing but a strip light. Okay, so strip means it's a two-dimensional source, and at the same point of time you are trying to ensure that light source is such that at each and every point it is giving the uniform intensity. Okay, and in the top portion of the tank what we have these green colored things are nothing but photodiodes. Okay, so these are different photodiodes. So what will be happening, this light will be passing through the medium and each of the photodiode will sense what is the height of kerosene and height of water corresponding to each of the diode, and accordingly it will be giving the value of the voltage signal. This point is clear? All these photodiodes are connected to a data acquisition system so that we can record the data of the voltage as a function of time. Okay, and of course here the light source is coherent, so we are trying to maintain that intensity of this light source is uniform. So is this setup clear? Now, because this particular setup, in this one of the case study we will be also seeing where we will try to utilize this configuration of optical sensors or photodiodes to even reconstruct the profile of curved surfaces. Okay, so in order to generate the curved surfaces, what is done, this entire test platform is placed on a rotating platform. Okay, so this is the schematic representation of the rotating platform, which includes a motor, then there is some coupling, and over this coupling, this with the help of some bearing, one total horizontal platform is made which can be given the rotation, and on this platform itself your light source as well as the optical sensors are mounted. Okay, now in this arrangement one slip ring assembly is used. The purpose of the slip ring assembly is because whenever you will be rotating the complete array, if your data acquisition system is not placed on the on your this system itself, then whatever the wires which will be connecting your data acquisition system to the photodiodes, what will be happening? Upon revolving, these wires will be actually twisting. Okay, so what we need to do over here, we need to place data acquisition system as well as the entire power assembly on this rotating platform itself. To assist that, this slip ring kind of assembly is used, which utilizes the fixed brushes. So say this is one brush, this is second brush, so one is positive terminal and this is negative terminal, and then in between this on the rotating shaft we have two terminals, one positive, one negative, and these two terminals now are rotating simultaneously with the platform, and brushes are making the continuous contact with the external power source. So in that case the entire power can be transferred to the rotating platform, and everything, your data acquisition system as well as the other equipment, you can mount everything on the rotating platform itself. Is this one clear? This is the photograph of this array. So here you can see the optical, these photodiodes are having inter diode spacing is represented by pitch P, and in total 10 number of diodes are used. So this is 1, 2, and likewise if you count the sequence, 10 number of diodes are placed in the linear arrangement. Okay, and these are the specification of the photodiode. So you can see here their photosensitive area is 2.4 to 2.8 millimeter square. Their spectral response range is 320 to 1100 nanometers. So it means if you give the wavelength of your signal in this range, corresponding to that it will be generating some voltage or current signal. Okay, and the photosensitivity of the photodiode is 0.52 amperes per watt at the wavelength of 780 nanometers. So it means 1 watt change in the intensity of the light source will be changing your current value by 0.52 amperes. Okay, and dark current of this photodiode is 10 nanoampere. So what is the meaning of dark current? If you place this photodiode in a chamber of complete dark where no light is present, corresponding to that whatever current output it will be giving, that is called as typically the dark current of the photodiode, or it is also called as saturation current. Is this one clear? Dark current or saturation current. So whenever you measure the current output of a photodiode, that is nothing but sum of its dark current plus signal corresponding to some supply intensity of light. Okay. So dark current is 10 nanoamperes. It means it is very small in comparison to the output. Let's see what is output in the next slide. So whenever we are using this type of arrangement, and our purpose is that for arbitrary voltage signal, we should be able to predict the height of the interface. Okay. So what we need to do before that, we need to actually calibrate this. So for the purpose of calibration, what is done here, you can see B is the height of the tank and Hx is the height of the kerosene. Okay, and this height of the kerosene actually we have taken as variable for the purpose of calibration. So initially you can see from this point, say I have initially started the experiment with some height. Okay, this signal is low. So say experiment is started something like this. From here to here, this entire was filled with the kerosene. So when entire tank was filled with the kerosene, corresponding to that you will be finding H will be equal to B. Okay. Once you have filled entirely with the kerosene, then corresponding to that, okay, let me check first. So what we have done, we have over here defined one non-dimensional parameter which is IW. What is IW? Current when tank is filled with water. Okay. So IW minus I is our arbitrary signal corresponding to the different heights. Okay, and that we have also again divided with IW. Okay, so in this way you can see that whenever my tank is completely filled with water, then corresponding to that what will be the value of signal? IW minus IW, which will be equal to close to 0. Okay. So let us consider that initially the entire tank is filled with water. Okay, initially entire tank is filled with water. So once entire tank is filled with water, then H is equal to 0, and corresponding to that my voltage signal should be 0. Now what is done? H is made equal to 1 centimeter and B, this spacing between the two plates is actually 10 centimeter. Okay. So once H is equal to 1 centimeter, then corresponding to this, my kerosene is only present in the top 1 centimeter portion and remaining 9 centimeter portion is actually covered with the water. So in this case, I will be having slight decrease in the value of I than the value for pure water. Okay, so once I am having slight decrease in the value, then IW minus I will be getting some small value. Okay, once it is divided by IW. So that is what we are getting over here. Corresponding to this situation, I am getting, so if I calculate H by B, it will be coming out to be 0.1. So for H by B of 0.1, if I start taking the current signal, so corresponding to this current signal, this is my data. So this is the signal from any single photodiode. Okay. Now after this, what I have done, from this point to this point, H by B was maintained close to 1. Then in the next step, H by B is equal to 0.2. So I have now filled the kerosene up to 2 centimeters. So in this scenario, what will be happening? If you have more signal, this value will keep on increasing more, and likewise you will be having corresponding change in the signal. So here you can see that at this point what you have done, you have opened the outlet valve and simultaneously opened the inlet valve. Okay. Once you have opened the outlet valve, water has started draining and its place was taken by the kerosene. Okay. So corresponding to this, what will be happening? This is the change when both the valves were open. Corresponding to this, your interface was moving in the downward direction. And once you have reached the value close to 2 centimeter, again you have stopped both the valves. Okay, once you stopped both the valves, you are again getting almost a constant. Then again what you have done, again switched on both the valves till you are getting to next 1 centimeter more kerosene filling in the tank. Okay, so in this way we have observed that when we are maintaining the interface at any stationary location, corresponding to that, what is happening? Corresponding to that, we are getting a constant value of the signal. And whenever we are changing the, continuously, gradually changing the height of the interface, corresponding to that, my signal is also changing actually gradually. Okay. So over here, because the tank is of same cross section, so in this case, the rate at which we are changing the height of the interface, that will be defining the flow rate of the water drainage and the kerosene entry. So that flow rate we can predict from the signal if we simply take the slope of this. So slope of the signal can be correlated with the data of flow rate while interface is gradually either rising or falling down. Is this point clear? So it means that whenever we are varying this at a step of 0.1, then we are finding our signal is actually gradually changing. Okay. And finally, when entire tank is filled, I am reaching close to h by b equal to 1, then the signal has got this value. One interesting fact you can observe that when for changing the same height initially, your difference between the two signal was large. But when we are reaching towards the larger height, corresponding to that, the difference in value of signal has actually decreased. And the reason for this is Beer-Lambert's law, which says that intensity will be decreasing in an exponential manner upon increasing the thickness of the particular type of fluid. Is this one clear? Now we can utilize this data. So here you can see, now this is the data corresponding to different height values. So this is h by b of 0.1 and this is h by b of 0.9. Is this one clear? So here you can see that when for the same change in step, how your value is actually changing. So initially your signal is more sensitive to slight change in height. Okay. But later on, in between these two steps, now the change is less. So change is less, it means sensitivity of the sensor has decreased. Okay. Is this point clear? Now what we need to do, because we need to utilize this signal for arbitrarily fitting our interface height. If we have any random signal known, then how we can utilize that signal to reconstruct the interface profile. So for that we have to develop one relationship in between the dimensionless current signal and corresponding value of the h by b. Okay. So for doing that, what we have done, during this entire cycle, whatever the average data of all 10 sensors is there, that average data is represented by these red colored circle points. Average data of all the 10 sensors. And corresponding to all the 10 sensors, whatever the standard deviation is there, that standard deviation is given as error bar in the signal. Is this one clear? So here you can see this is the dimensionless current signal and this is our h by b. Now if we fit this data, so h by b equal to 0.048 into e power 4.134 of phi fits this relation well. So it means that if you know the value of phi, which is dimensionless current signal, for any arbitrary interface configuration, Corresponding to that, you can put the value of phi and you can observe the corresponding height in front of that particular sensor. Is this one clear? So now here you can see some of the predictions. So as I told you that initially some platform is used, and once we use the platform, what platform will do? It will tilt the box, and when we are tilting the box because of the gravity, so you have to consider that gravity is actually operating in this direction. Okay, so this photograph over here is actually placed in a rotated manner so that gravity is pointing in this direction. Because if you consider a tank, and in that tank if you fill two fluids, two liquids, so heavier will be at the bottom and lighter will be at the top, and if you tilt that tank, what will be happening? Upon tilting the tank, you will be finding that interface will be remaining only horizontal, but the portion in these zones will be different with reference to the tank surface. So what we have done, we have placed light source like this and sensors also like this. So it means when we are rotating the tank, then sensor as well as the light source both are changing with reference to the tank. So it means that whatever the value of height we are measuring, that is with reference to the top surface of the tank. Is this point clear? So once it is with reference to the top surface of the tank, then the data obtained from the sensors should be able to give us the representation of the interface height.
So, but if you are measuring the height from the surface of the sensor, then we will get a variable height.
Yes.
So the graph would be different than what you already have.
So here, yes, earlier graph will not be there, but now you can see over here, this is the photograph. So in this photograph you can see water is at the bottom and blue colored thing is kerosene, and this theta is close to 10.65 degrees. So here you can see this is your interface, and in this interface everywhere the height of the kerosene is different. Now what are these points? These scattered points are nothing but the predictions from the optical signal. So whatever optical signal we have obtained phi, for each sensor that phi we have substituted back, and from that phi whatever data we have got, that I have actually plotted over here. So now you can see for each sensor value of height is different. So is this one clear? All are clear with this idea? Now you can see that if your interface is straight and you have 10 number of points, then you can simply use the linear interpolation between these 2 points to know the interface boundary between these 2 points. Is this one clear? Because if we are working with the straight interfaces, then what will happen? In between the 2 data points, I can simply join a straight line. So over here for these 10 sensors, I have actually fitted a straight line using the best fit curve, and this straight line you can see is matching well with the photograph which is captured with the camera from the side. Okay, and now you can see this signal is also shown for another angle of 13.72 degrees. So here also you can see, and this is the graph which shows that the angle which is specified, like which is measured from the camera, or which we have specified while we have changed that particular platform, and this is the angle which we have obtained from the data which is linearly fitted using the optical signals. So here you can see this is the 100% accuracy line, black line, and these scattered points are very close to the 100% accuracy line. So it means this type of optical arrangement has been used successfully for reconstructing the profile of the straight interfaces. Okay. Now we have to also see what is the sensitivity of this device for dynamic measurements. Okay, so in the previous discussion, what is done? In the previous discussion, whatever we have done till now, we have oriented tank at certain angle and then it was kept stationary. Okay, but now if we give certain motion to the tank in such a way that interface keep on oscillating like this. Okay, so say I have dropped the tank from certain height. After that, what has happened? This was my interface. Interface has started oscillating. So it was going something like this. Now what will be happening? If I consider this is the center point about which interface is oscillating, and say I am trying to capture the data from some optical signal which is here. So this height will keep on changing with time. This height will keep on changing with time. So at each and every time, value of height signal will be different. Whenever interface is moving in positive direction from mean position, then value of height signal will increase. And once interface is going in downward direction, then value of this height will decrease. Okay, so likewise here you can see this is the phase fraction and this is my time. If I plot the phase fraction as function of time, then for any signal this blue colored line is the position of the interface as function of time which is captured from camera. Okay, and all these red colored circles are data which is obtained from the optical signals. Okay, so here you can see even for dynamic measurements, optical signal is very well able to determine the signal, determine the evolution of the interface height. Okay, and in case you do not have any forcing mechanism which is keeping the interface to continuously oscillate, what will happen? After certain time, the amplitude of the interface oscillation will keep on decreasing and finally it will settle down to its initial situation. So that type of signal we are easily able to capture using this optical measurement. Is this point clear? So it means that this type of test confirms that the data measured from the optical signal can also be used for measurement of the dynamic interfaces. And this you can see one example. So this red colored line, this red colored triangle is for sensor which is mounted at a distance of, so this is your x, okay, where what was the reference of x, do you recall or do I need to explain? So you can see here the center of the first sensor is your x. Now here you can see x by b equal to 0.72 is your blue line, x by b equal to 0.84 is your black line, and x by b equal to 0.96 is your red line. Okay, so here you can observe that for black line, what is the value of the signal? Almost stationary. It means that this is the location which is our pivot point about which interface is oscillating up and down. Is this point clear? Because whenever interface is moving like this, so I have some point about which interface is oscillating up and down. Okay, and the location of this point is actually not changing with time. So that is something which we are able to observe. Whenever we initially start the oscillating process, what is done in this experiment? The tank is dropped from certain height so that the oscillation can initially start. So there will be some initial disturbances because of which the pivot point may deviate slightly. So these initial interface oscillations are captured well, and after certain amount of time, the initial interface disturbances have actually died down, and now the tank or the interface is oscillating about a fixed pivot point. Okay, so x by v equal to 0.4 is my pivot point. Now you can see x by v is 0.72. So 0.72 is on the left side of 0.84 and 0.96 is on right side of 0.84. So what will be happening? When interface is like this, then the value for 0.72 will be less and value for 0.96 will be high. Is this one clear? So here you can observe now, whenever I am having peak for one, so here you can see this is the peak for one and fall for the other. Okay, is this one clear? Because one is on left side of the pivot point and other is on right side of the pivot point. So when interface is moving in like this, so this for this particular detector now height is less, so there is decrease in the height. But for this detector height of the kerosene is more, so that's why when height is more, so it is giving the higher. Okay, and we have phase of 180 degrees in between the two heights. And other than that, interesting point is this 0.78 and 0.96 both are at equal distance from each other, so their amplitude should be having the almost the same magnitude. So here this difference and this difference are almost the same. Is this one clear? So it means that if you have a straight interface, but that straight interface is dynamic, then also this type of optical arrangement can be used. This is the third type of system. So what was the third part? We had placed entire platform on a rotating system. Okay. So whenever we place it on a rotating system, because of the rotation, what happens? Heavier fluid will be moving in outward direction and lighter fluid will be moving in the inward side. And because of this, we will be finding the presence of a curved interface, something like this. Okay, and these are the 10 sensors. So here you can see these scattered points are the data obtained from the 10 sensors, and photograph is showing the actual interface configuration, and this dashed line is data which is fitted from the by using polynomial fit between the 10 sensors. Okay, and here also you can see whatever the pitch for sensors you have used, that is sufficient enough to properly capture the curvature of the interface. Is this one clear? And of course this is done for different RPM. So here you can see RPM was less and here RPM is more. So once you have more RPM, then curvature will be actually more, and that steep curvature also the optical signals are able to capture nicely. Okay. This is some random pattern which is generated in the interface, and upon generation of the random pattern you can see now your interface profile is very intricate, but still if you will be fitting the best fit data, that will be going something like this. Okay, so the portions where interface profile is not very complicated and it is well stratified, there it will be able to properly capture it, but in the portions of significant fluctuations in curvature, whatever the spacing we have between the two sensors, that is not sufficient enough to capture the very complex profiles. Okay, so in order to improve accuracy in this system, what we need to do? We need to have more data points. If we have to go for the more data points, then whatever the size of the photodiode we have taken, we have to consider more thinner photodiodes, because then only we will be able to closely place them. Is this one clear? Now next is this data of phase fraction can also be useful for measurement of the flow rate. Okay, so here you can see that in this tank we know that from top we have inlet and from the bottom we have outlet. Okay, so if I allow the fluid to flow from top to bottom, so from top I am allowing kerosene to flow and from bottom I am allowing water to flow, and the area of the tank is same, then flow rate can be written in terms of area into change in height of the interface. Okay, now change in height of the interface, I can vary this height of interface by changing the value of the flow rate. If I use less flow rate, then change of height with time will be slow. But if I use more flow rate, then change of height with time will be more. So that you can observe over here, this black colored line is corresponding to flow rate of 0.11 lpm, and all the other lines are on increasing order of the flow rate, and maximum flow rate is 1.6 liters per minute. And here you can see that whatever the set value of the flow rate we have measured from other devices like rotameter or so, that is my supplied flow rate, and this is the flow rate which is measured by taking the slope of this optical signal. So the slope of optical signal is giving these scattered points, and this is the 10% accuracy line, dashed line is 10% accuracy line which is drawn. So you can see that the flow rate measured is within the order of 10% of accuracy. And here you can see the strength of the signal. So what can happen, it may happen that initially we were operating at some different flow rate, and then in between the measurement itself we have actually switched from one value of flow rate to the other value of flow rate. So here you can see that whenever you do such altercations, then your sensors is immediately able to respond to this type of sudden changes. Okay, so still whatever these experimental cases are shown over here for interface reconstruction and flow rate measurement, their interface movement was not very high. Okay, so interface movement was, the time scale of interface movement was less in comparison to the time scale at which your photodiode was responding to changes in the intensity of the light. Okay, in case your time scale of interface increase is significantly high in comparison to the response time of the photodiode to light in photovoltaic mode, then photodiodes can also be used with the help of some more electronic circuits in photoconductive mode. So typically in photoconductive modes, the response time of the photodiodes can go up to the frequency range of gigahertz. So gigahertz means even your micro or nanoseconds changes in the interface evolution can also be captured using the photodiodes once these are operated in the photoconductive mode. Okay. So this was just a case study that whatever we have discussed the fundamental ideas, how these fundamental ideas we can employ in the practical scenarios for the interface reconstruction, etc. However, in this discussion, the major idea was that we were trying to construct the interfaces only in the stratified regimes. Okay, if we go for the more complex situation like bubbly flow, etc., for example, in case of bubbly flow, what will be happening? This light has to pass through the two interfaces, so their measurement of height, etc., will be becoming even more challenging. So whatever the simple exponential relation and the linear or polynomial fitting we have done, that may not be sufficient enough to properly capture the interface profile. So we have to go for even more sophisticated measurements, as well as the algorithms for reconstructing the interface profile should also be more sophisticated. Okay. So this is brief discussion about the uh, determination of flow designs and interface reconstruction using some optical methods. Now we will move to next type of measurement, which we call as velocity measurement. Okay. So all of you know that. First, can you tell me by using which type of devices we can measure the velocity of the single phase flow systems? So orifice meter typically gives you the average value of the velocity. Okay, so for example, if flow happens through a pipe, what happens? We have two velocities. One will be the local velocity, which varies in parabolic manner for a laminar flow situation, and another, what I can do, I can consider the assumption of one dimensional flow, where at entire cross section of the pipe I am defining some average representative of this velocity variation, which is called as average velocity. So typically orifice meter, venturi meter, these are the devices which gives you the measurement of the average flow velocity. Okay, but if you have to do the velocity measurement, okay, then majority of time our interest will be to know the local value of velocity, because in case of multi-phase systems, what will be happening, the different dispersed phases will be present in the different portions, and in different portions of the tube, each of the dispersed phase particle will be having different surrounding velocity field. Okay, so that's why our in situ or local measurement of the velocity will be essential. So in terms of single phase flow measurement of in situ velocity, whatever in your basic fluid mechanics you study, we only study about pitot tube uh, apparatus. Okay, where with the help of changing the location of the pitot tube, we can actually know the local value of the velocity. Yes. There are many advanced methods such as particle image velocimetry, laser Doppler velocimetry, hot wire anemometry, etc., which can be employed for measurement of the velocity field at large number of points in the flow field. So what is the general principle of all these type of devices, that we will try to discuss in this discussion. And again, after discussing their general principle, we will also try to see what are the additions we need to do in these devices or in these methods, so that these can be extended for measurement of velocity in the multi-phase systems. Okay, so first point is, velocity measurements in multi-phase systems are more challenging in comparison to the single phase system. This you know, because we have large number of particles available. So these particles have multiple interfaces. So if you are using the optical techniques, then there will be multiple scatterings of the lights, whereas in case of single phase flow, the scattering of the light will be from same type of medium. So all these things will be actually making the measurement of velocity challenging, particularly for multi-phase flow systems. So we have interest of velocity measurement for some peculiar structures such as gas bubble or liquid slug, etc. So different type of structures are present in the multi-phase systems. You have already seen in terms of flow design maps. So in order to know the behavior of that particular structure, we may need to determine the velocity. So the advanced velocity measurement techniques which we can employ, some of these are laser Doppler velocimetry, hot wire anemometry, and particle image velocimetry. Among these techniques, hot wire anemometry and particle image velocimetry are suitable for multi-phase flow applications. Laser Doppler velocimetry is not that much suitable for the multi-phase flow measurements. What is the reason? Okay, there are some other alternate methods as well, such as cross correlation technique and digital image processing techniques, etc. Okay, but what is the challenge of LDV measurement? So LDV typically works on the principle of frequency shift of a laser beam which is scattered by a moving object, and this is something which we call as a Doppler effect. So if we have a moving object, there will be change in the frequency of the signal which is passing through that moving object. So typically in two-phase flow systems, if we have any laser beam, that will be also scattered from the interfaces other than just the continuous phase which is moving. Okay, so because of this, what we observe is that the strength of the signal which is observed, that decreases significantly, and it becomes challenging to understand the difference between noise and the actual signal which we have obtained. So due to this reason, typically LDV is only used when we have very low concentration of bubbles or droplets in the system. Then we can use LDV. But if we have significant number of bubbles and drops present in the system, then value of the signal which is obtained at the sensor will be so small that it will be almost acting like a noise. Okay.
So then why do we use LDV at all for multi-phase flow if it is not giving correct values?
We don't use it. So that is the reason. So in the initial days, whenever people have started, so they have tested with the small concentration, because when they go, when they went for the high concentration of the bubbles and other particles, then it was not working. Okay, so let's little bit discuss the mathematics. What are the primary measurements which we need to do? So capital UK is average velocity in kth direction, and this is equal to 1 by AK, where area of the cross section in kth direction, and integral over the area UKX into dA. What is UKX? Local velocity in kth direction. And why local velocity? Because you can see with this UK, we are using one argument x. What does this argument x is representing? It is representing position vector x I cap plus y j cap plus z k cap. Okay, so it means we are pointing to a particular position. For example, in single pipe case, what we do? If pitot tube is placed at this location, then I am obtaining the value in the kth direction at some position x1. When I am keeping pitot tube at this location, then I am measuring UK at some position x2. Likewise, once I have data for different positions, then I can do area averaging of that data and calculate the average value of the velocity. Is this one clear? So small UK over here is local velocity in kth direction, and capital UK is area averaged velocity. So you can simply understand that from pitot tube, whatever velocity you are measuring, that is your small UK, and from the orifice meter or venturi meter, whatever velocity you are measuring, that is your capital UK. This I need not to explain. This is nothing but our superficial velocities. This is also we have studied already, drift velocity. One more parameter also becomes essential in multi-phase flow measurements, which is called as slip ratio or velocity ratio. So this is nothing but the velocity, average velocity of the gaseous phase divided by average velocity of the liquid phase, and it can be correlated in terms of volumetric flow rate of gas divided by volumetric flow rate of liquid into 1 minus epsilon by epsilon, where epsilon is nothing but my void fraction. Okay, so slip ratio becomes essential sometimes in defining the value of drag, lift and other type of forces which are exchanging between the dispersed and the continuous phases. Okay, this is again representation of slip ratio in terms of mass quality and void fraction. So if we know this basic idea about these parameters, after that we can actually go for the measurement of velocity. So
जो लोकल वेलोसिटी है वो आपने जो पहले लोकल इंस्टेंटेनियस वेलोसिटी पढ़ा थी दोनों सेम है या अलग अलग?
if this local velocity ukx is calculated by considering 1 by t integral over the t uk xt dt, then it is local velocity and uk xt is actually local instantaneous velocity. Is this one clear? Yes. So whenever uk I am only putting position, it means at that particular location I am taking sufficient time to measure the velocity and doing and using a time averaging velocity value. Okay, but if you simply just your flow is very random and at each and every time you are trying to record the value of velocity, that will be becoming local instantaneous velocity, and in that case you have to write it uk as function of x bar comma. All are clear with this idea? Okay, so maybe I'll stop at this point and we'll discuss further in the next class.